Hi, everyone, and thanks everyone for coming out today to our ACOM seminar. I'm really happy to introduce Steve Montzka today. Some of you know Steve has been working at NOAA for so many years now, here in Boulder, in the Global Monitoring Division throughout his career. So he leads a program making global scale atmospheric measurements of many compounds, many chemical compounds from flask air samples collected at over a dozen remote sites around the world. The chemicals that he and his group measure include greenhouse gases, ozone-depleting gases, and air pollutants. So the results are relevant to many important issues of our time. But as he mentioned, the real reason he has remained in this position at NOAA for nearly 3 decades is that the results from his program supply interesting and unique scientific and policy-relevant insights into the working of the atmosphere and the natural and human processes affecting it. Thanks, Steve, for coming out today, and looking forward to your presentation.
Thanks, and thanks for the invite. And it's good to be here. I'm glad you could come. Boy, even some people from my lab, one person anyway, great. Yeah, so in my opinion, I think they lead to interesting scientific insights and policy-relevant insights. And so I'm going to talk today about one particular issue, and that is this emissions of CFC-11, a banned ozone-depleting substances. Are those emissions really increasing? And I'll talk a little bit about what's being done about it also. And I certainly owe thanks, but haven't listed all the co-authors on a couple papers that have appeared in the past year and a half related to this issue. And also, I can never forget to thank the station personnel at NOAA and cooperative sites around the world helping with the flask sampling and instrument maintenance. You know, they're the ones out in the field that allow us to get the samples, make the measurements on the in-situ instruments at least. And the AGH community of scientists for a nice collaborative effort. So, despite a warning nearly 45 years ago about chlorine and ozone-depleting substances, and the universal ratification of the Montreal Protocol on substances that deplete the ozone layer, the ozone layer is far from recovered. You know, here's a picture of the ozone concentrations as a function of altitude over South Pole last fall in October. And the red line is an ozone flight on October of 12th of 2018. These are ozone sounds by colleagues at NOAA. Red line's what was observed. You see plenty of ozone depletion in the 15 to 20 kilometer region. It's a little bit, yeah, okay, so I gotta work this out here. There's not a pointer here. There is, no. Okay, and compared to the green line, which is the regular or pre-ozone hole profile for ozone, and the 1991 to 2012 averages given there in black. So there's still substantial ozone depletion. So why do we consider the Montreal Protocol perhaps the most successful international agreement ever? Well, adherence to the protocol has led to a couple things. One, near elimination of ozone-depleting substance production, and that's shown here over time for CFCs in red and all ozone-depleting substances in blue, and this is weighted by ODP kilotons, so a ODP-weighted mass. And the CFC production reportedly was phased out in 2010 per Montreal Protocol, although minimal production was reported even by as early as 2007. These are values reported to the Ozone Secretariat that I've replotted here. So the second reason is declines in ozone-depleting emissions and concentrations are observed. That's what we do, and right here I show the concentrations of ozone-depleting chlorine over time and ozone-depleting bromine. And this is based on our tropospheric concentrations of CFCs, HCFCs, chlorinated solvents, methyl halides, and halons. See, the chlorine has come down on the order of 12 to 13% since its peak, and the bromines come down on the order of 2 to 3 ppt. So substantial declines as a result of the protocol and the controls on production. So the projections that have been made are that pre-ozone hole concentrations of ozone-depleting substances will be reached later in this century. But an important caveat, and that is provided continued adherence to the protocol's controls on these ozone-depleting substances. So, as I mentioned, at NOAA, GMD, what I've been doing for nearly 3 decades is tracking ozone-depleting gas concentrations globally. We have a number of different sites where we do this around the world. The white points are where we get weekly measurements from flasks, paired flask samples typically. And there's a few sites where we get hourly measurements from in situ instrumentation of a subset of gases. Measure about 40 different gases, including the ozone-depleting substances, of course, but also other gases now controlled by the protocol, including HFCs, other methyl halides, other polychlorinated and brominated hydrocarbons, benzene and other hydrocarbons, carbonyl sulfide. And we use these results, of course, to assess the efficacy of the Montreal Protocol, but also to provide scientific insights. For example, related to global atmospheric oxidation variability, carbon uptake by the biosphere, looking at carbonyl sulfide, non-CO2 greenhouse gas contributions to radiative forcing, climate sensitivities of natural processes influencing the concentrations of these gases, and atmospheric transport processes. So here's a summary in terms of hemispheric means of 4 different gases out of the many that we measure. We have CFC-11 and methylchloroform, the original gases on the left that were controlled, original ozone-depleting substances, primary ozone-depleting substances, controlled by the Montreal Protocol. And you can see the concentrations decreasing. I guess the methylchloroform is particularly interesting because the decline is essentially linear on a log-log scale. It's been an exponential decay of methylchloroform now for for over 2 decades. And it's from that we infer things about the atmospheric oxidation capacity over time and its stability. And the substitutes, HCFC-22, first generation substitute chemical. And you can see that it was increasing, accelerating its increase, but now it seems to be on its way towards a plateau. And that's probably because in 2013, production was mandated by the protocol to be capped in 2013. And maybe we're starting to see a result of that in the atmospheric concentrations. And then the next generation substitute, HFC, here's an HFC 134A used in car air conditioners, but also in other refrigeration capacities, is increasing, and increase is at least constant, if not accelerating over time still, since those longer lived, higher GWP HFCs are in the protocol as being controlled, but that will happen in the next few years. So CFC-11, the production phase out globally was in 2010. In developed countries, it started in 1996 as being phased out. But the production phase out was in 2010 globally. And what do we see after that? We expect an accelerated decline in the atmosphere, but what do we see instead? Instead, we see that the concentration decline slows down. And that's what I've spent my last 2, 3, 4 years working on quite intensively. And so that's what we're going to talk about today. So on the left side here, we have the abundance, the growth rate, and the hemispheric concentration difference for CFC-11. In the abundance panel, the colors represent hemispheric means, and there's different colors and multiple lines given the fact that we measure it 3 different ways. And you can see that all 3 of those different ways showed a slowdown in the decline. These thin lines, if you can see them, they're what was projected for CFC-11 concentrations over time, and that clearly didn't happen. The growth rate, it was declining at minus 0.8% per year, and that has slowed substantially. And from that growth rate, we know, and from other things, that significant emissions of F11 persist despite it being its production being phased out. And that's because it was used in foams. There's a large reservoir of material in foams, maybe even in these chairs here. Probably not much left there, but that is retained, that it slowly escapes to the atmosphere. We also know that there's still substantial emissions persisting for F11 because the decline was 0.8% per year. Its lifetime is thought to be about 50 years. So we'd expect it to decay in the atmosphere 1/50 or 2% per year. And it's less than half of that. And it's slowed down, so that's much less than half of that. There's plenty of F11 still in the atmosphere. It accounts for 20 to 25% of ozone-depleting chlorine in the atmosphere. This decline observed between 2002 to 2012 was the largest contributor to the overall decline of chlorine during this period. It was methylchloroform before then, and the CFCs have taken over that role as being the force for declines in atmospheric chlorine and ultimately recover the ozone layer. It was the largest, and the slowdown after 2012 was accompanied by an increase in the difference between the hemispheric mole fractions. So you can see that here. As the slowdown occurred, the north to south difference increased. I need to wear my mic if I move away from that, sorry. And we published our paper right about here. So what do these results say about CFC-11 emissions globally? Well, if we just apply a simple mass balance approach towards the concentration that we measure and use that concentration as an estimate of the global atmospheric burden of CFC-11, and consider mass balance where the rate of change is equal to how much is going in, emission versus how much is lost each year. We know the global burden, G, and its rate of change over time. At least we infer it from what we measure at the surface. If we assume we know the lifetime of F11, in other words, the loss rate, then we can derive global emissions, and that's what's shown here over time. Each point is an annual emission rate derived from the burden and rate of change from one year to the next. And I've shown that relative to the reported production, decreasing, as we mentioned before, to 0 in and around 2007 to 2010. And you can see that as the concentration decline, let's see if I can pull this up here. As reported production was decreasing, emission was also decreasing similarly initially, but production continued to decline to 0 and emission remained fairly constant. And then after that time, emission even increased, as derived from the measurements when the concentration decline slowed. So our emissions increased from this simple mass balance approach. It appears that yes, an emission increase around 13 gigograms a year is implied after 2012. And that's for the average of what we've derived for the emissions during 2014 to 16. But the key here is this lifetime. One key, anyway. Is that easily treated as a constant over time? Or is it easily treated as a constant loss frequency in a 3-box or 12-box model? And we spent a lot of time with some 3D modeling folks with some help also of Doug, I believe, through Peng-Fei Yu, Bob Portman, and John Daniel, other folks in the Chemical Sciences Division of NOAA, to try to understand how much of this apparent, or how much of this observed slowdown, apparent emission increase, is actually due to maybe changes either in the lifetime of F11, or if you think about it a little bit differently, we measured at the surface the losses in the stratosphere, and so there could be interannual variations in how that loss signal reaches where we measure. So when we considered that, we came up with this answer that, well, maybe dynamical changes persisting through these 3 years might have contributed to about half of this apparent emission increase that we've derived. Now, as time goes on, we expect long-term changes potentially in dynamics owing to changes in greenhouse gas concentrations. But as time goes on over, not 20 to 30 to 40 years, but 3 to 5 to 10 years, this signal and its persistence becomes more directly and more completely attributable, we think, through additional analyses, especially by these guys, to primarily an emission change, not a dynamical change. A smaller contribution to dynamics than what we talked about in the initial paper, and that it was up to half. Okay, if we look at this and say, shoot, Steve, that's a pretty small little change you're talking about there. Well, let's also consider what we expected for emissions over time. We expected emissions, because production goes away, we expect this reservoir and a certain percentage of it to escape the atmosphere each year, so that that reservoir becomes smaller each year, so the emissions that come from that reservoir also you might expect to become smaller from that year. That's what the dashed line is, or if you follow the atmospheric record for a few more years, that's what the gray solid line is there. And so it's actually what we're observing, 25 to 30 gigagrams per year above what we'd expect to have happened in recent years, so a significant amount. Okay, the next point is that emissions aren't illegal under the protocol. We can emit different amounts of ozone-depleting substances, and it may be illegal according to your national laws, but according to the protocol, they care about production, and they care about international trade, which is also called consumption, which is the sum of production plus imports minus exports. So the next question is this the result actually of new production, or is CFC-11 escaping more rapidly now than it was before from this large reservoir of material? I showed in the previous slide emissions of around 50 gigagrams per year. That reservoir is thought to be on the order of 20 times larger, 1,200 gigagrams in 2012. And Susan and some of the students Megan Lickley, have been working on refining our estimates of understanding of these bank magnitudes. So there's a big reservoir, a certain small percentage of it leaking each time. If that leakage rate were to be enhanced, we would see potentially this in the atmosphere too. Can we address that at all? If you consider the emission record, and we have this independently determined bank, we know production amounts, and we know how that bank should decrease. If we take the emission divided by that bank magnitude, we can derive what these records would imply for the loss rate from the bank from year to year. How rapidly is the bank, this reservoir of foam, how rapidly is CFC-11 escaping from it? And that's what this line is, the implied release fraction each year from that bank. It was decreasing in the early years, well, from 1995 to 2005, potentially, maybe as the more emissive reservoirs of this material were depleting themselves. But then, if this production record's right, that escape rate would have to have nearly doubled since the early 2000s. And talk to industry folks, business folks, there's no evidence to suggest that this has happened. And so it seems highly unlikely, points to the fact that these results strongly suggest actually an increase in production of CFC-11 since the phase out in 2010. So in violation of the Montreal Protocol. So let's consider updated results. We published this result 2018. It used and made estimates of emission for 2016. And the red points here now are an estimate for 2017 using just my results and a simple model analysis, and a preliminary update for 2018. And this implies that the escape rate would have to be now on the order of 9%, so even more unusual and unlikely, still then continuing to point to new production. Let's also consider this cumulative excess emission. This is around 200 gigagrams of material, a lot of stuff. And the key question here is, it's just a lot of stuff. And but depending on how the CFC-11 is being used, since it was used primarily for foams, and when you make a foam, most of the CFC-11 that you use to make that foam stay in the foam, only a small fraction gets released to the atmosphere. Does this imply actually that there's been a lot more production? And in fact, the industry folks who are looking at think that it's most likely that CFC-11 during this most recent period in a particular region of the world has been used for foam. So it could be that this is a signal of much larger rates of production. We'll talk some more about that in a minute. Okay, so based on our measurements, we've identified that CFC-11 is not going down. We think it's from actually a violation to the Montreal Protocol. Can we tell at all where this emission increase is happening from? I mentioned that we make measurements in these locations. We also make measurements with enhanced frequency and density over the US. And we use these results with inverse modeling to assess US emission rates so that we can understand US contributions to global emission changes that we have observed using our global network. And when we do that, and we make lots of measurements over the US, it implies no significant emission increase over the US, at least from the period from, and this is the work of that nice young lady back there, Dr. Who works in GMD with me, and by herself, but I'm happy to collaborate, have been very happy to collaborate with her over time. We did an analysis through 2014 that suggests a significant decline in CFC-11 emissions. And the measurements since then, while they haven't been carefully looked at yet, but will be soon, suggest that emissions, if anything, continue to decrease after that period of time. And similar conclusions have been drawn for the Northwest Europe by Alistair Manning. So the two most industrialized regions where most of the CFC-11 was used, we have actually some high-density measurements over those regions suggest that they aren't the cause of this emission increase that we're observing on a global scale. So where have they increased? Well, turns out air reaching Hawaii in autumn can be influenced by Eurasian emissions. And we make measurements. On top of the Mauna Loa station, we looked at these measurements carefully and found out that before 2012, the pollution plumes reaching Hawaii did not contain elevated concentrations of CFC-11. But after 2012, they did. And I'm going to show you a little bit more about that. So here, how do we identify pollution plumes? Well, we measure a bunch of anthropogenic gases, things like HCFC-22, dichloromethane, carbon monoxide, known to become anthropogenically produced and emitted gases. And here we have HCFC-22 concentrations during 2 different years. The second half, it's like the latter half of the year, 0.4 of the year, 0.4 of the way through the year through the January 1 for 2010, 2016. And we can see that in both years, HCFC-22 concentrations were varying similarly. The scale has changed, but the range here is the same in both of these years. And so we see variations in anthropogenically emitted gases at Hawaii. How about CFC-11? In 2010, not much variation, not as much as HCFC-22, at least on this scale, and certainly no correlation in those variations. And here's the regression coefficient for a number of different years, not just 2010, shown in this plot here. But in 2016, there's a strong correlation. In fact, the regression coefficient increases substantially during that time, as does the slope in the slope between these two chemicals, suggesting that after 2012, these pollution plumes do contain elevated CFC-11. And it wasn't just that the dynamics changed unusually, since the correlations observed between HCFC-22, dichloromethane, carbon monoxide, and other gases, they were similarly sustained and similarly high throughout all these years. So CFC-11 changed in a unique way. So could we determine the source region for these pollution plumes that were reaching Hawaii? And this is just one way to express it. I'm looking at back trajectories, looking at surface regions influencing a sample as it's collected in Hawaii. The darker shading indicates those surface regions. And I averaged that surface region during the 2013 to 16 period where lower concentrations of HCFC-22 and F11 were measured. And you can see that we have high sensitivity due to background atmospheric oceanic marine boundary layer. The higher concentrations, though, are associated with surface sensitivities over Eastern Asia. And so this allowed us to conclude that those higher concentrations are associated with air from Eastern Asia. In other words, implying an emission of F11 from Eastern Asia beginning in around after 2012, concurrently with the global emission increase that we've derived. So, since the paper came out, well, as we were working on this, we knew and were aware of many other folks making measurements of CFCs throughout the world, especially the A-gauge community of folks. And we're fortunate that measurement stations also exist in Eastern Asia. And these two sites, Gosan and Hataruma, are in that region. And we're going to look more carefully at the A-gauge and Korean and Japanese measurements made in this region of the world. Just a little picture of the Gosan station so to remind you that as air comes from the west, or the Yellow Sea, we get pretty much unfettered, clean air, marine-based air coming without local influences. And here are those results since 2008 now through 2018, where the discrete air sample results are plotted from Gosan on the top for CFC-11 and Hataruma in the bottom. And if you look carefully at these measurements, and also 40 degrees south, Cape Grim from the CSIRO A-gauge instrument is shown in the gray, might be difficult to see, for reference. And you can see that when you look at the differences between the sites, there's clearly evidence for lots of emissions in and around Eastern Asia. And this isn't surprising since there's a large bank of CFC-11. It was only phased out in 2010. We expect continued emissions, but what we don't expect is an enhancement in the concentration of F11 in these pollution plumes as they're reaching this site over time. And so that's an anomalous increase over time, one that also starts a little bit after 2012. Increasing the elevated, at the Gosan station. Hataruma, it's a little less clear. There are some enhancements, but it's not as obvious. So we can summarize those measurements by year in box and whisker plots. So the black lines, the median, I have the 25th to 75th percentile shown by the size of the box, and the red lines are the 10th to 90th percentile. And if you look carefully at the Gosan measurements, either in the size of the box before and after 2012, or in the difference between these red bars, you can see that these concentration enhancements were about 2 times higher on average after 2012 than before. And all else being constant, that would imply an emission increase, maybe a doubling of emissions upwind of this site. At Hataruma, the signal's much more subtle, much less obvious. It also implies that if there's an emission increase from this region of the world, it's impacting Gosan a lot more strongly than it is the Hataruma site. And just a reminder that increasing variability like this is not observed at any other NOAA or A-gauge site around the world. Now, that doesn't mean that this is the only place around the world where emissions are increasing, because those measurement locations don't have high sensitivity to all populated or all industrial regions of the world. For example, India is not covered, Indonesia is not covered, Russia is not covered, Africa is not covered, South America is not covered. So we've identified, it appears, one region in the world where emissions are increasing, but we can't comment on all the other regions put together, or all the other regions individually. We do have a picture of global changes, of course. So Matt Rigby and his modeling friends published a paper in the spring of this past year looking at these, interpreting these measurements with inverse model analyses. And they used 4 different models to estimate the location and magnitude of emissions from this region of the world based on the measurements at those 2 sites. Here's the Gosan site here, and here's the Hataruma site. And if you look carefully, you maybe can see this hatched portion. They were only comfortable making estimates of emissions for the regions that were close to these sites, so the regions that don't have that hatching. If that makes sense. And so here is the average emission from 2008 to 2012 for this region of the world. And you can see there's some emissions from these different regions, and there's some degree of consistency. There seems to be emission from this peninsula, at least in 2 of those, maybe 3 of those, some hint of it here. Let's look at the next 4-year period, and that's 2014 to 17. Color scale is the same. Darker blue shading indicates more emissions, and you can see substantially enhanced emissions for that region in essentially all these different inverse approaches. And this is the difference, where in that lowest panel, the red is the region of increased emissions, and the blue are the regions of decreased emissions. A fairly strong signal of increased emissions from particularly two provinces in China, the Shandong and Hebei provinces, consistently shown to be an increasing source of CFC-11 by all these inverse analyses. So this seems to be a pretty strong indication that emissions have increased from China. And the next question is, by how much? And so now we're going to focus on just that area surrounding these sites, the land-based area, that these modelers felt comfortable with, that they felt had enough sensitivity to determine emissions from. So we're going to determine emissions from that region. And I might note that includes all of South Korea, most of North Korea, about half of Japan, and a region of China that encompasses about a third of its population. So not all of China, but just this region of China, highly industrialized, lots of chemical processing, chemical plants going on there, but only a third of China. And this is what they get. So we have emissions. The different colors there are emissions from these 4 different inverse analyses compared to what they expect from an inventory-based analysis. Although this inventory was a total China inventory analysis scaled by that population factor. But in all 4 of these these inverse approaches conducted by the team of modelers who were using their own expert model, their own model to do the inverse analyses, all show an increase in CFC-11 emissions that appears to be about 7 plus or minus 3 gigograms a year, which is consistent with the near doubling of concentration enhancements observed at the Gosan station. So that's about that change of about 7. And so let's compare that to this global change. Here we can see that if we just look at each inverse analysis and look at the uncertainties associated with them, each one of them derives a significant emission increase over time. And how does that compare to the global change? And this is a global change. It's the average of emissions in all these instances of 2014 to 17, that average versus a 2008 to 12. It's a little different time period of reference from what I included in my original paper. But you can see that there may be some differences there. The increases globally, I have here from somewhat less to 11 to 17 gigograms a year. And I say somewhat less because of this issue of dynamics. The potential for dynamics to cause or add to what we infer about emissions based on atmospheric concentration measurements at the surface. So it might not be a global increase of 11 to 17. It might be somewhat less given that contribution of dynamics. And the increase derived regionally from this portion of China is around 7. And so what was said in the paper is that Eastern China accounts for at least 40 to 60% of the global CFC emission increase. So what are the implications for the ozone layer? We have CFC-11 renewed production and increases in emissions. And if the problem is rapidly fixed, the impact on the ozone layer should be small. If these emissions continue into the future indefinitely, the ozone recovery delay could be 7 to 20 years, depending on which region of the atmosphere you're considering, mid-latitudes or polar regions. Now, given all the attention that this has garnered, this seems highly unlikely. But consider that the magnitude of the problem ultimately depends on the magnitude of unreported production. And we don't know what that production magnitude is, given what I mentioned before, in that the most likely use seems to be, at least the industry experts from the Technology and Economic Assessment Panel of the Montreal Protocol suggest that it's most likely been used for foams, so that indeed a significant fraction of the production hasn't yet leaked to the atmosphere. So it's going to sustain and could sustain emissions despite effective mitigation actions on any new production in the future. What happens to the bank of foam is another thing. And that factor might be on the order of 2 to 3. So what we've observed for an emission increase or unexpected emission, if it were all for polyurethane closed cell foams, it could be 2 to 3 times larger than that. So there was lots of reaction to the results. On-the-ground investigative reporting by the New York Times and this organization called the Environmental Investigation Agency. And they found by going to China and clandestinely interviewing folks that there was evidence for ongoing use and production of F-11 in China. But the overall quantities weren't readily discernible. They're not well known from a survey. The Environmental Investigation Agency did a survey of a number of producers and users of F-11, but a very small fraction of the total. But they concluded in their rough analysis that it could be suggested that in 2018, most of the closed cell foam industry in China had reverted back to using CFC-11. But this wasn't a scientific analysis. It was just an extrapolation, a consideration of what was possible. So the parties to the Montreal Protocol considered the findings, and they've had 3 meetings now. They meet twice a year. They have every year since the end of the 1980s met to understand how the Montreal Protocol can be amended and adjusted, how it should be amended and adjusted to ensure that the ozone layer heals. And this is pictures here are of the president of Ecuador came to open the meeting as it took place, the meeting of the parties in last November. And you see the science assessment panel, and including Dave Fahey, I missed him in this picture, and one interloper over here. And I've been to these past 3 meetings. I was fortunate enough to be able to go to present the science to the parties in different side events and to be there to answer questions that they might have, which has been very, very enriching. So the remaining question is relate to what is being done. And the Montreal Protocols are taking a number of different actions, and they relate to, one, taking the issue seriously. They've spent these meetings, big fractions of these meetings, spending time studying this issue. They're looking for more information. External meetings have been held. Reports have been requested from the science communities through the Science Assessment Panel and the Technology and Economic Assessment Panel, which are the industry folks, the business folks, to answer questions like, what will the ozone layer impact be? Are emissions increasing outside of Northeast China? What has led to this issue? What conditions economically, governmentally led to this issue that allowed renewed production of F-11? And how is the CFC-11 being produced? Is it small mom and pop shops, or is it big industry? And of course, they're interested to facilitate the rapid mitigation of this issue. They're also reconsidering money being transferred to China. You think about the leverage that the parties to the Montreal Protocol has, a lot of it has to do with this multilateral fund. Money from developed to developing countries to facilitate the phase out of ozone-depleting substances. And over time, since the 1980s, China in particular has received about $1.3 billion US dollars to facilitate the phase out of production. And in their most recent requests for funding, which took place in the spring of this past year, that funding was deferred. And a large part of the reason it was deferred was because of the concern by the parties in the room about the F-11 issue. So that's some degree of leverage over making things happen. They're also considering, I've read some documents in different transcripts of different meetings, considering punitive action, maybe even remedial action with respect to what you do with the current control schedules, but also considering amendments to the protocol to prevent future violations in the future. Certainly with respect to ozone-depleting substances, but think about HCFCs being phased out currently, and a good deal of those HCFCs also still being produced for allowed purposes. And so it'll be a matter between discerning, here's production going on. For CFCs, it's probably, for CFC-11, it doesn't have any allowed uses. Any production meant an illegal activity. But HCFCs used in the production of Teflon, that will continue and continues to increase actually. And so it'll be very tricky then to understand, okay, we have production, but is it for all allowed purposes or for something else? The same thing, it'll even be even trickier for HFCs because it's only a phase down. It's scheduled to be a phase down based on GWP equivalent emissions. So there will continue to be some ongoing production and a transition to other less climate active HFCs. And so you can imagine similar, if not larger, challenges to monitoring the adherence to these control schedules in the future. Okay, China's response. China, to their credit, has repeatedly indicated a commitment to work with other countries, scientists, and industry experts to locate and eliminate the true source of the increased CFC-11 emissions. They have conducted lots of inspections of enterprises or businesses across the country and found instances of illegal production and use. And they indicate that they've prosecuted those responsible. But the amounts that they've seen so far and been able to discern and have shared with us have been small. They found 29.9 tons of newly produced CFC-11 and 10 enterprises using CFC-11. This was since August of 2018. This clearly doesn't seem to be enough to account for what we're seeing in the atmosphere. So they formulated a plan of action, and they formulated this plan of action even before the Rigby et al. Paper that came out that actually fingered China. My paper originally said, or the paper that I led, I should say, originally said, we think an emission increase is coming from Eastern Asia. We don't know which country, and we don't know if it counts for all of the emission increase. The second paper, led by Matt Rigby, was able to quantify those things, as I showed, and pinpoint them to China. But even before that second paper came out, they came up with this plan that has a number of different things, including developing national scale atmospheric monitoring of ozone depleting substances and HFCs, so that China can be in a position to understand their own problems as opposed to somebody making measurements outside of China, pointing and telling them how it's going. Seems to me a good thing. They've built 6 testing laboratories to understand whether or not, if you want to know if this foam was blown with a banned substance, you can bring it to this testing laboratory and have that determined. They've strengthened inspections and enforcement. Another key thing, though, is better tracking of carbon tetrachloride, which is the source material used to produce any CFC, a methane-based CFC. And carbon tet is produced in large quantities throughout the world because it's produced in a train of chemical production of chloromethane production. Chloromethanes, you take methane and chlorinate it to produce things like methyl chloride, dichloromethane, chloroform, and also carbon tet is unavoidably produced. It's used for a bunch of different things, but that stream allows there to be some that could be taken for other uses, for example, making CFCs. And so if that was better tracked, maybe that would help eliminate the source of any available carbon tet for CFC production. New programs to enhance enforcement, facilitating reporting of non-compliance by industry. They're going to try to get competitors to point, this fellow is selling something really cheap over here. CFC-11 is cheaper than the alternatives. Are they using F11? Maybe they'll tell the Chinese environment boards to go over there and poke around. Turns out this has been shown to be an effective way for industry to police itself. And this last one I find kind of interesting, extending penalties to end users for non-compliance. I bought a chair today and I'm sitting in it, feels great. And somebody comes and tells me it was blown with illegally produced CFC-11. I'm now the one that's culpable. Okay, so just to conclude here. I have been part of this program for a long time. This was the most surprising thing that I've ever seen in making measurements for nearly 3 decades, and was happy to be in a position to be able to detect this. And To imagine atmospheric monitoring enabling the early detection of a significant violation of the Montreal Protocol and the indication of the location of a renewed source of CFC-11. I never thought I'd be in this position, actually, because I never thought we'd be able to understand how the change in the atmosphere with emissions, how we could precisely determine the expectation relative to what we measured. But it became pretty clear that emissions going up after production was phased out indicated something was amiss. And also that atmospheric monitoring have led to the parties to the Montreal Protocol to consider potential revisions to strengthen this protocol. That's all good. But the path to rapid and lasting mitigation remains still unclear, as there are other regions potentially contributing to the increased CFC-11 emissions. The network system that we have out there isn't potentially extensive enough to account for a number of different regions, and so far we've only identified half of this global emission increase. And an important point is that the delay in ozone recovery is not yet well constrained because of this issue related to production magnitudes. We detected what reached the atmosphere. We don't know how much was actually produced. And more broadly, considering the future, you ask yourself as scientists, is our atmospheric vigilance capability up to the task, either with respect to observations or modelers, or models? Think about the global emission rate of change, think about global measurements and discerning emissions from that. The parties in particular are very interested in knowing ASAP how emissions are responding to all this activity and the plans by China. And so we're ready to take our updated measurements and tell them. And yet we can't necessarily discern how emissions have changed from year to year because of the influences of dynamics on what we measure at the surface, how that loss signal reaches the surface. So that's incumbent upon us as scientists, as modelers, to hopefully be able to take atmospheric measurements and provide more information about both the source contribution and the sink contribution on a year-to-year basis more accurately. And so I think that's kind of a task for us as scientists to try to work on, try to improve. Especially since we have phase outs for HCFCs and phase downs for HFCs, and the elephant sitting in the room somewhere over here, greenhouse gases, whose budgets are much more complex given that they include substantial amounts of natural emissions. And they can potentially change independent of human-related processes. So to conclude here, if we hope to provide actionable information to policymakers in the future, I think our science capabilities still need substantial improving, especially in the ability for us to quantify, locate, and attribute emissions on global and regional scales. And so with that, thanks for your attention, and happy to take questions if there's time.
Thanks, Steve. Are there any questions?
Thanks, Steve. It's very nice talk. What is the major obstacle in establishing the monitoring network over like India, Africa, South America?
Will, money, and dedicated expertise. The Carbon Cycle Group has 40 different sites around the world where they make measurements. And they're always trying to get more measurements in regions that are poorly sampled. And it's always extremely difficult because of those reasons. We, in recent years, have phased out, terminated sites because of our own NOAA internal funding. To ask developing countries to do this is very difficult too, because a lot of those regions are developing countries.
Thank you.
There are more questions?
So, Steve, you've done great work here. You talked
Thank
about
you.
3 different numbers.
Yeah.
You presented 3 different numbers for the magnitude of the issue, if you want to call it that, right? So 7 is what you think you can account for from Eastern China based on the Rigby et al. Paper. But then you had a global number of 18, and your, quote, difference from expected number was some very large number, like 35, it can't possibly really be 35, can it? I mean, how do you reconcile the 35 and the 18 is one question, and please reconcile the 18 with the 7 for me as best you can.
7, yes, 7 plus or minus 3 for Eastern China. 11 to, I thought it was 17 for the global change between 2008 to 12 versus 2014 to 17. And the 25 to 30, and that was just an increase above a constant. So, yeah, but as time goes on, we think less and less, that fraction has to be smaller and smaller. The dynamicists who I'm talking to say it just can't be half, it's got to be a lot smaller number. In fact, it's probably, in fact, as we look at some of the modeling analyses that we did before, the models that we believe more suggest less influence of dynamics. So maybe 11 to 17 in those two periods, and that's a constant baseline. And the 25 to 30, I think, not quite 35, was this expectation based on how the bank might have been expected to behave to sustain emissions over time, decreasing. So not, it's a delta versus a constant was the 11 to 17 based on, and those two numbers forgot to qualify that. One was derived from the NOAA measurements, and one was derived from the A-gauge measurements. So the two different global networks give you a little different number, but the 25 to 30 was relative to some expectation. Does that help?
I knew that was what you were doing. But,
yeah.
25 to 30 is just, it's
you,
enormous number. I mean, it's just very difficult for me to even imagine that expectation has any validity. I mean, why are you even putting it out there? It just seems like, floating the idea that there's 4 times more sitting out there being emitted somewhere else. I mean, that's huge.
It is huge. I can't explain it.
Very difficult. Isn't it much more likely that the expectation was just wrong, that the bank is bigger, or that the release rate is different? I mean, there's so many ways to reconcile it.
That's why in my paper, I didn't include any expectations. It was just a delta versus a constant. That's exactly why I did that. But how do we expect these banks to work? It is a big question, I agree. And if we expect them to work in a way that is a certain percent per year, that's what you'd expect. Is that right or wrong? Maybe indeed it's not right. And the other key thing about, or unusual thing about this, which maybe provides hints to what you're suggesting too, is that even from 2002 to 12, why didn't the emissions decrease during that period? Yeah, is that a misunderstanding of how the bank processes work, or is it some small contribution of what we've seen become quite larger in more recent years?
Those are. It's really big.
Yeah.
And the amount that's going into the atmosphere is relatively small compared to that.
Yeah.
And it can stay fairly constant for quite some time. Very difficult.
It would go down very slowly. I agree. Yeah.
So I just think we really need to be careful on this, particularly since you haven't seen a concomitant change in 12, or have you?
No. Yeah. Susan mentioned CFC-12 because when you take carbon TED and produce CFC-11, the expectation is the typical reaction conditions are that you also produce CFC-12. In fact, for every 2 moles of CFC-11 you produce maybe about 1 of CFC-12. And yet the results from these sites in Eastern Asia don't show any emission increase in CFC-12. Does that mean there's no production? We have I've given you the story of why we think there's new production. Does it mean the CFC-12 has been used for something else that's less emissive, like refrigeration type of applications? Is it used as a feedstock for producing some, I think it was Halon 1301? These are all questions. I mean, there's a whole list of questions here. I showed you a couple of them. There's still many puzzles out there left to ponder and to pontificate over. Many of them are less related to what we do each and every day, and a lot related to what the industry experts their best estimate of things. But there are still plenty of things to do in the scientific community. Like what I suggested here. Yeah.
There is one more question.
So the leveling off of the concentrations in, what was it, 2005, when the concentrations become level, is that the inflection point between when production ceases and the emissions from the bank continue?
Well, let's be clear, Julia. Concentrations are still decreasing. It's emissions that plateau during this period. I mean, we're just talking about this with Susan's response. So this is emissions. The concentrations are still going down. Sorry.
Yeah, I apologize, I misspoke.
Right.
I meant the emissions.
All right. So emissions stop going down. Maybe okay. There's noise. There's interannual variability. Did it come down and over? Is it just if you draw a curve through there? Is it just nice slowing down? That's the timing. I don't know much more about it than you just looking at it there. There was a shift in developing country production, and it happened right around that period of time, maybe peaking in the 2000 to 2005 era. But that's objective information that we have. The developing countries, when they produced CFC-11, it was during that period of time.
Just a quick question. The interhemispheric gradient, is that reproduced well by the 3D model in which you estimate a change in the lifetime?
It's reproduced fairly well by the 3D models. But it's not perfectly reproduced. This influence of dynamics that suggests, let me start over. The influence of dynamics that's suggested is only reflected in the rate of change. Those models, those 3D models, where we look at the change in north to south, they can't mimic what we've observed without an emission increase that's substantial, right? But the thought is that the interhemispheric difference is a much trickier thing to try to model than a global rate of change, and so most of the discussion that we've been focused on is that.
The lifetime, presumably, is due to how quickly you get the CFC-11 up to the height where it polarizes.
Well, I would also suggest that it may not actually be a change in the lifetime. It may be an effect of how rapidly that loss signal makes it to the surface. You can get differences in transport at different regions of the stratosphere, I am told. I am not the expert in this, but low branch circulation enhancing, maybe blocking off some of the high branch circulation back down through the polar region in the springtime. It's too complicated for me to understand completely, but that's why I'm relying on some dynamic folks for sure.
So just to follow up on this question of transport, which maybe I didn't get right, you seem to imply that the actual emission increase rate may be lower than it appears because some change in dynamics. But couldn't just as easily be higher? I mean, why would the effect of dynamics tend to increase the apparent rate of emission? I mean, why couldn't it be the other way? I mean, I don't know what the dynamics that takes CFC into the stratosphere, to the lost region, how that has changed in this very short period of time. We know that over long enough periods of time, the Brewer-Dobson circulation ought to be accelerated, especially the shallow branch. So if anything, that should make TF-11 shorter, right?
Mm-hmm. Yeah, exactly. We inferred that direction based on the 3D model analyses. Based on the 3D model analyses, that's what suggested it, that the effect was you could do model analyses with constant emissions over time, and the concentration would slow down. The concentration decline would slow down on its own based on the dynamical changes. It was based on that modeling analysis. Now, you look at this emission record, you see ups and downs and things like that. Are those real? And on the long term, I think we could be pretty confident that emissions decreased and then kind of turned over and then gone up again. But these interrelated variations, people like Eric Ray, in fact, are studying them quite carefully to understand the QBO influence on what we measure at the surface. And maybe some other influences, how the QBO interacts with different strong El Niños, other things like that. And does that signal persist is it more than just can it persist over a few years' time? And at this point in time, we were looking at 3 years, 2014 to 16, and that's, yeah.
There are more questions? Following up? If not, let's thank again Steve.